All right. Another optimization method, numeric one, is called golden section search. Golden section search. It's used as an optimization method. And first, it's important for us to talk about what the golden ratio is. So the golden ratio is the idea that if you have a rectangle, okay, if you have a rectangle and you were to draw a square in this rectangle, then the portion that remains has the same proportions as the original rectangle. Okay, that is to say that the short side of the big rectangle, okay, the short side of the big rectangle has a length of 1, okay, and the long side of the big rectangle has a length of 1 plus x. And then once you remove this square over here, now we have a smaller rectangle, and the short side has a length of x, and the big side has a length of 1, okay? So the ratio between x and 1, that is the short side and the long side of the little rectangle, is the same as the ratio between 1 and 1 plus x, that is the short side of the big rectangle and the long side of the big rectangle, okay? So here's, and this will continue, that if you take this smaller rectangle and you cut a square out there, okay, so that is this side has x and this side has x, and now you have 1 minus x here, okay, the ratio between 1 minus x, that is the short side of the little rectangle, okay, to x, that is the length of the little rectangle, okay, will have the same proportions as, say, x to 1, and the same proportions as 1 to 1 plus x. So if you take any of these ratios, okay, the yellow to the yellow or the blue to the blue, they're all going to have the same kind of proportions, okay? So if I say, the length of the blue divided by the length of the red, okay, it will be the same as the length of the blue divided by the length of the red for the smaller rectangle. So for the big rectangle, the length of blue is 1, and the length of the short side is 1, and the length of the long side on the big rectangle is 1 plus x. Okay, if you look at this side over here, okay, the length of blue, okay, the length of the short side here is x, and then the length of the long side on the this little rectangle is 1. And so you have 1 over 1 plus x is equal to x over 1. And so now we can solve for x. So you have 1 over 1 plus x is equal to x. And you solve for x, so you multiply both sides by 1 plus x, and you get this quadratic equation, x squared plus x minus 1. And so solving for where this is equal to 0, you can use the quadratic equation, negative b plus or minus, all right? And so you'll get negative 1 plus or minus this, and we'll use the positive sign, okay? So we get negative 1 plus root 5 over 2, and we get x is 0.618, approximately. X is 0.618, and so we can see that if I do 1 divided by 1.618, we get approximately 0.618, okay? Another interesting thing is that if you square 0.618, 0.618 squared is equal to approximately 0.382, which is the same as 1 minus 0.618, okay? So if you do 1 minus x, that's equal to x squared. So if you do 0.618 squared, you get 0.382. All right, so let's, so with that in mind, regarding the golden ratio, we can use the golden ratio for golden section search. Okay, so here's a simple function, x squared minus 0.8x, okay, where a minimum's at 0.4, and what we want to do is we want to minimize this. We want to find this minimum location of 0.4. Well, here we just have the graph here. So here I'm going to just start off with an interval. We'll go from 0 to 1, and we'll say, okay, we know there's a minimum value somewhere between 0 and 1, and we want to try to find out where that minimum value exists, okay? So I have my left-hand bound side, which is 0, my right-hand side is 1, There's a minimum somewhere in between 0 and 1, and we're trying to figure out what that location is. So what I'm going to do is I'm going to draw kind of two interior lines. Okay, the interior lines are determined by using the golden ratio. So if you have your left-hand side and your right-hand side, okay, or your lower bound and upper bound, I should say, I have my lower bound and my upper bound, okay, my golden ratio is approximately 0.618, so I'm going to go 0.618 from the lower bound to the upper bound, 0.618 of the way, and that's going to be location x1. And I'm going to go 0.618 of the way from the upper bound down to the lower bound. So basically this location x1 is going to be the lower bound plus 0.618 times, the difference between u and l. And then this location over here is going to be the upper bound minus 0.618 times the distance between u and l. Okay? So those are going to be my two locations. So here, if my left-hand side is 0 and my right-hand side is 1, my x1 is 0.618 of the way, so I'm at 0.618. And then here I'm 0.618 of the way on the way down to 0, so I'm at, 0.382. So I'm going to evaluate 0.618 and 0.382. That's going to be my values for x1 and x2. And so what I do is I calculate the value of the function at 0.618. That's going to be f of x1. And I calculate the value of the function at 0.382, f of x2. And what I find is that f of x1 is greater than f of x2. f of x1 is greater than f of x2. So what that tells me is that I can then throw away, I can shrink my interval, and I can say I'm going to search for the minimum value between 0 and 0.618. The reason why is, remember, the original premise is that we have a minimum value between 0 and 1. And I evaluated two locations here. And here I know that f of x2 is less than f of x1. And so I'm going to say there has to be a value between 0 and x1 that is less than f of x1, and we know it because it's at least f of x2 or something less than f of x2. Okay, and so I can throw away everything to the right because if there's a minimum value, we know the minimum value is on the left hand side too. There's at least x2. At x2, there's a value that's less than f of x1. So I'm going to just ignore everything to the right. So I'm going to throw away to the right. Okay, so because f of x1 is greater than f of x2, we know that the minimum must lie between L and x1. Okay, the minimum value can't be to the right of x1 because we know a value x2 exists between L and x1 that produces a smaller value. So we eliminate the value to the right, and now I'm going to search for my minimum between 0 and x1, 0 and 0.618. Okay, and what I'm going to do now, okay, is I need to find basically my two interior points. Now this is where the beauty of using the golden ratio comes in, okay, because I need to find a location that's 0.618 of the way from 0 to 0.618, right? And so that's 0.618 squared, which is 0.32, which is going to be this exact location. And then I need to find a value of 0.618 from here down to 0. Okay, so I got to figure that out, okay? But by using the golden ratio to determine my interior points, I can reuse this point over here because I want to go, remember we're going 0.618 of the way from the left bound side to the lower bound to the upper bound. And so if I go 0.618 of the way up to x1, which is located at 0.618, that's going to give me 0.618 squared, which is exactly where x2 is located. So that's what I have here, right? So my new x1, my new kind of interior point here is going to be the lower bound plus phi times the new width of our interval, okay, which is going to be 0.618 squared, or 0.382, and that was my old x2 value. So I'm going to reuse this value. I don't need to actually recalculate any of these numbers. These have already been calculated for us because I calculated them in the previous step. And so this is going to save me some computational power. Okay, I do have to calculate this location. So this is going to be u minus 0.618 squared, and that's going to give me 0.236. So I do have to calculate this location, and I calculate the value of the function at that location. And I see that this value, the value of the function here, is higher than the value of the function here. So I'm going to throw away everything to the left over here. Okay, so I throw away everything to the left of that location. And again, now I can reuse this value, right? This is going to be become my new x2. And I'm going to have to calculate a new x1. So I'm going to have to calculate 0.618 of the way over here. From here to here, that's going to be my new x1 value. And I'll calculate that. And that gives me this. This is slightly higher than this one. So we'll throw away everything to the right of this. Okay? And when I do that, okay, it bounced up, but we'll eliminate the side between x1 and the upper bound, and I will reuse this value right here, okay, and that becomes my new x1, and I have to calculate this one. And so this is higher than this location, so we're going to throw away everything to the left here, and what you'll see is that this location right here will get reused as one of the interior lines. So we're going to throw away everything over here, and the line that was there, okay, got reused. We calculate a new thing, right? So between these two, I'm actually not sure which one is higher or lower. So, but we run the algorithm, and it says, okay, apparently this one was higher, so we're going to throw that one away. We will reuse the line right here, and this is what we have. We'll calculate this. This is slightly higher, so we'll throw that side away, and we'll reuse the line right here. And we keep going, and eventually, you know, the intervals just keep shrinking and shrinking and shrinking, and you get smaller intervals, and at some point you can say, all right, this is the left and the lower bound and upper bound are near enough together that I'll go ahead and stop, and that can find your minimum value. So the golden section search method is actually very robust. It's kind of like bisection method for root finding, but golden section for optimization, finding a minimum. Okay, if there is a minimum in the interval, it will find the minimum. Okay, if the minimum lies on the boundary of your interval, okay, it will eventually converge to the boundary point. And if you have multiple minima inside your interval, then it will converge to one of those local minima. Okay, you have a few termination conditions as far as like when do you want to stop searching, right? And I would say a common choice is when the difference between the upper and lower bound is less than some arbitrary tolerance. So you can say when the lower and upper bound have a difference of less than 10 to the minus 5 or 10 to the minus 6, that's when we'll call it quits. Okay, so here's code that you can use, and you can see that it does exactly what we said, right? So the golden ratio is -1 plus square root of 5 divided by 2. That's going to give us approximately 0.618. We need to provide a lower and upper bound, okay? And then my tolerance where it's going to quit is going to be 10 to the minus 5. So we're going to find our interior points. x1 is the lower bound plus phi times upper minus lower, and x2 is the upper bound minus phi times upper minus lower. And the arrangement of points is going to be lower, x2, x1, upper. We're going to evaluate the function at x1 and x2. That will give me f1 and f2. I'll start off at just iteration 0. And then we're going to run this while loop. And it's going to keep running as long as the difference between the upper minus the lower is greater than our tolerance. Okay? And so first we'll check to see if f2 is greater than f1. Okay? If this value is greater than this value, then we're going to throw away basically everything to the left of x2. We know that the minimum has to be between x2 and the upper bound. So x2 is going to become my new lower bound. x1 is going to become the new kind of interior point, x2. And then I'll reuse the function f1 that I calculated to be my f2. I don't have to recalculate that. I do need to calculate a new location of x1. That's going to be kind of using my new lower bound plus phi times upper minus lower. Okay, that'll be x1, and I do need to calculate the value of the function at x1, and that will become my new f1. Okay, and that's the end of that, and we'll run the loop again. Okay. On the other hand, if f2 is less than f1, then we'll throw away everything to the right, and the minimum has to be between the lower bound and x1. So x1 will become my new upper bound, x2 becomes the new x1, the new interior point. I'll reuse the value of f2 that I calculated earlier. I don't need to recalculate it. So the f of f2 becomes f1, and then x2 becomes, I have to calculate the new value of x2, which is upper minus phi times upper minus lower, and then we'll calculate f2 for there. Okay, we'll add 1 to the number of iterations, and we just keep going. All right, and then it keeps running. At the end, we'll say it converged in this many iterations, and the value we will return will be the midpoint of the lower and upper bounds here. Okay, so here if I say let's search for a minimum of the function x squared minus 0.8x, okay, just from algebra we know the minimum is going to be at 0.4, and we'll see. So if I run this between 0 and 1, it took me 24 iterations and I got 0.3999999. If I want my tolerance to be smaller, 10 to the minus 6, it takes me 29 iterations. 10 to the minus 7 takes me 34 iterations. 10 to the minus 8, it takes me 39 iterations to get there. Okay, the width of each iteration basically shrinks the size of my interval by a factor of 0.618. After 2 additional iterations, the width of the interval is less than 40% of the original interval. And one thing you might have noticed is that increasing 1 decimal place of precision, going from 10 to the minus 5 to 10 to the minus 6, I needed an additional 5 iterations. Going from 10 to the minus 6 to 10 to the minus 7, I needed another 5 iterations. And that's because if I do phi to the 5th power, that's going to give me around a little less than 0.1. So if you want your interval to shrink by a factor of 10, it's going to require approximately 5 additional iterations. So that's what we have there. Okay, that is the golden section search. Pretty powerful method for finding minimums of a univariate function. Might be a little bit slow, but it certainly works.